All right, we are recording.
All right, I'm good to start.
Yes, Jordan, you're good.
Okay, perfect. Sorry, guys. All right. Hello, everybody. SIMIO Aerospace Simulation Project, done by Group 7.
This is
Role
Andrew
numbers.
Crabtree.
Hmm?
Jacob Cox.
Hey guys, I'm Jacob Faltimar.
Jordan DeFreitas.
And Kevin Episcopo.
Today, just briefly, we're going to go over the introduction and problem statement for the current problems that SIMIO Aerospace is facing. SIMIO Aerospace currently is using a rigid 4-day cycle for moving planes down their production line. This causes what is known as travel work, where regardless of their completion, unfinished tasks are passed down the production line. In addition to this, SIMIO Aerospace wants to introduce a third plane type known as the SA-103 within their current facility without costly expansions. Overall, the goal of this project will be to improve efficiency and test the feasibility of integrating SA-103 into the simulation. Some objectives to consider. We want to definitely look at eliminating or reducing overall travel work. In addition to that, evaluating different buffering and processing configurations, as well as testing workforce flexibility and shift schedules, and overall assessing SA-103 integration without costly facility reconfigurations. For the input data overview, the sequential tasks for data for the 5 workstations, which is taken from the SIMIO Aerospace data file provided to us. The labor assignments being the number of mechanics per task, the shift definitions being the 2 active and 1 inactive that we currently have to work with, as well as the plane types, SA-101, SA-102, and SA-103, which has the same task data as SA-101.
Hey, I'm Kevin, and for this project, I was working on the basic rudimentary parts of our SIMIO model. So to set it up, we have a source, and they go through the 5 server nodes, 1, 2, 3, 4, and 5, each with their allocated employees to them, which are set to their own work schedule. We also have our 3 entities, which is the SA-101, SA-102, and SA-103. And as Jordan said, oh, you can go back. As Jordan said prior, the SA-101 and 103 are going to be the same triangular distribution modes that were set for each task. And then we also have our exit node. You can go to the next slide. So some basic stuff we set up was the work period on the top left is the work schedule, which has the standard set schedule, which has 1 hour and 30 minutes of break in between all the shifts. And we had to set the value to 8. This is something that we messed up on our initial SIMIO model that we had to fix now because we have to allocate 8 resources towards that shift. So that's why we had the value 8 there. On the top right part is where we have actually, I'll go to the bottom left. On the bottom left is where we have the different mix values for our planes. So with the SA-101 showing 60% of the time, SA-102 40% of the time. And this is going to change with our later experiments where we have to switch the SA-103 into effect and have a certain cap for the planes going. And on the top right is where we have our reference models for each task. So initially we had one giant table with the key values of 101, 102, and 103. And this wasn't working because we needed to separate every like the priority number by task, because originally it wasn't reading that there's priority numbers depending on whatever server way it went to. So we had the idea of separating it by task 1, 2, 3, 4, and 5. And these tabs were all separated into the different server or into the different employees that we had previously, to where employee 1 would be focusing on their own task, which was connected to the server. And then the same goes down for employee 2, 3, 4, and 5. And then, as stated previously, this is the interpretation that we had, which was given to us on the file, which is our triangular distribution modes for every single task, having the low, high, and middle. Those were set 1 to 20 for the first couple, and then server 5 was set 1 to 5 because it only had 5 tasks allocated towards that. Our plane mixes before that we talked about, and the schedule differences in time for each station, which was changed depending on the experiment that we were trying to run.
I'm Jacob Cox. Our modeling approach and assumptions are we're assuming that no travel work is allowed. The task must be completed before moving. The models test different buffer sizes and processing capacities, that's shown as above what Kevin has stated. All shifts switch instantly. There are no warm-up delays. As both Kevin and Jordan have stated previously, our SA 103 was modeled identically to SA 101, and our production line is going to be starting empty with 0 capacity.
Hey guys, so Jacob Faltmeyer here. And before jumping into any analysis, we made sure to verify and validate our SIMIO model. So first, for verification, we ran multiple test simulations step by step to make sure the model behaved as expected. Then we checked that each plane followed the correct task sequence at each work cell, and that planes didn't move forward until all tasks were completed. We also reviewed worker assignments to ensure that the number of workers matched what was required based on the task data. Then we ran a few trial scenarios, including some extreme cases with fewer workers, just to make sure the model responded logically and didn't break. So even without the full results, we're confident the model was set up correctly. And then for validation, we looked at expected outputs based on our 3.5-day plane arrival schedule. Even though we didn't get full simulation data, early runs showed that throughput, blocking, and worker behavior all made sense for how the real system would likely perform. If we had more time and could really get our model correct, we would have validated using more complete production output comparisons.
This is Andrew Crabtree. I'll be covering the scenarios we tested. Scenario 1 was no buffers between cells, which we predicted would cause high blocking idle workers and long cycle times. Scenario 2 was 1 plane buffers between cells, which we thought would reduce blocking, moderate improvements with flow. And then for scenario 3, we did unlimited buffers, which we thought would have the best cycle time and best batch completion, but high work in progress. And then scenario 4, we did 2 plane capacity per cell with no buffers, strong performance, efficient, but without large buffers. So here we have no buffers between cells, where 2 shifts were used for the workers, 5 employees were assigned to each station, and the buffer capacity was set to 0. Station capacity was set to 1, as you can see right there. The buffer capacity was set to 0. For this next one, we had the buffer space between cells was increased to 1, and then all other variables were kept the same. Next, we had unlimited buffer space between cells, which you can see right there as the capacity of the input buffer is put to infinity. And then finally, we also did stations with capacity of 2, where the buffer capacity was once again set to 0, but station capacity was set to 2. So 2 plans could be worked on simultaneously in each station.
Hey, so Jacob Faltmeyer back here again. So first off, as part of our initial work, we focused on analyzing the processing times and labor hours for both SA 101 and SA 102 models across all 5 work cells. What we found is that SA 102 is slightly more efficient overall, mainly due to shorter task durations and a better distribution of labor requirements at several stations. While our full scenario testing is still in progress, these early findings already give us valuable benchmarks. They'll help us compare how changes such as adding buffers, adjusting shifts, or making worker assignments more flexible, they actually impact performance. So even though we don't have final numbers yet, these initial outputs give us a solid reference point. And as we continue testing, we'll be able to build on these insights and develop more reliable recommendations for improving the system.
Jacob Cox here again. Our recommendations are to implement 1 plane buffer between work cells. That it's been shown from our initial calculations and what we suggest would be better based off of previous testing. We would allow selective worker flexibility in early task stages. We would actually introduce third shift or weekend overtime to support SA 103 as we're adding another airplane into the facility. It makes sense to add an extra shift just to allow increased production of that product. And then avoid expensive facility expansions by optimizing within our current layout. We want to make sure our cost is efficient within our product and our simulation. Final thoughts. While we weren't able to get our full results for this simulation, we were able to provide valuable insight into our system efficiencies and what if scenarios. We're able to provide data-driven recommendations to what we are providing to our stakeholder. And then this model is able to be reused or adapted for any future planning and expansion within SIMIO Aerospace. This is our final project. Hope you enjoyed, and thank you.